today's video we're going to be learning about Hardy-Weinberg Equilibrium and the disruption of Hardy-Weinberg Equilibrium. The initial number of each of these mice in their population is represented by this chart that has their genotypes and the alleles that are in those genotypes. For us to determine if these mice are in Hardy-Weinberg Equilibrium, we must first determine the frequency of the alleles in this population. We do this calculation right here, which is 2 times 30 because there are 2 of the big F alleles in this genotype, plus 70 because there's 1 of the big F alleles in this genotype, divided by 280 because there is twice the number total alleles in this population. And then we repeat those steps for the little f allele, and we get the allele frequencies over here. Next, we can determine the genotype frequencies, which for big F, it's just this f value squared. For big F, little f, it is 2 times the f value times the little f value, and for little f, it is the little f value squared. Next, we're able to plug these frequencies into a chi-squared table to determine whether or not these mice are in Hardy-Weinberg Equilibrium. And in this chi-squared table, we have the observed frequency of the mice,
next we can determine the genotype frequencies,
which is the total of the population
big F,
times
it's just this f value
the
squared.
frequency
For big F, little f, it is 2 times
the
f value times the little f value, and for little f, it is the little f value squared.
These numbers over here, which we add together to get this final total number. And this is the number that we're going to compare to our critical value, which is 3.841, which we determined by finding our degrees of freedom, which is our number of genotypes minus our number of alleles. And our total number over here is less than our critical value, which means we're all good and that we are in Hardy-Weinberg Equilibrium. Other factors that go along with Hardy-Weinberg Equilibrium, and that is that there is random mating in this population, no selection, no migration, and no mutation. And the law that we're going to be disobeying today is the no selection law. When we add in our selection, we get these fitnesses for each of the genotypes. With this type of selection, you can see that the 2 extremes are the highest fitness values, while the center is the lowest fitness value, so that means we have disruptive selection with underdominance, where they're moving away from the heterozygous genotype. And then we can take these fitnesses in order to determine the frequency of this population after selection. So here we have our initial frequencies, we have our fitness values, and then we can use these to determine the unadjusted survivors. To do this, we just multiply our initial frequency times our fitness to get the unadjusted survivors. And we do this for each genotype. We add them together to get our average fitness in this population. This average fitness is used to determine the relative frequency of each genotype after selection. And we do this for each genotype once again, and each of these add together to get 1, which is good. That's what we want. So now we can determine the frequency of each allele after selection by taking this new frequency of the big F, and adding it to 1/2 of the new big F, little f frequency, because we're only worried about the big F for this calculation. And that gives us this new frequency of the allele. We repeat those steps for the little f, and we get this new frequency of the allele. So this type of selection spread the alleles more evenly as the alleles move towards the 2 homozygous extremes. So in this population, we selected away from this colorful mouse because it would attract more predators, and therefore the mice would want to select away from it for these 2 extremes, the solid mouse, which can better blend into their environment. And through this selection, they are taken out of Hardy-Weinberg Equilibrium.